So please go through the total topics whatever we have discussed regarding transmission lines. Now further we continue with the concept of travelling waves in transmission lines. Concept of travelling waves in transmission lines. So to explain this, you consider a dam located, further a hydroelectric power station, and further we have the water flowing in the downstream. So consider now the water flowing after generation in the downstream. Say let it be for agriculture or domestic purpose. The water flowing in the downstream, say maybe agriculture or domestic purpose. Now you throw stone in this water flow. Throw a stone in this water flow. What happens? A part of the water is reflected back. A part of the water is reflected back. And some part of the water still flows in the downstream without getting reflected. A part of the water gets reflected and part of the water still continues to flow in the downstream without getting reflected. So we have two parts. A part of the water flowing without getting reflected. What you call it as? You call it as incident water. And a part of the water is reflected. Part of the water is reflected. And you know, is the reflection permanent? Very temporary. After the reflection is completed, again the reflected water flows in the downstream. Again the reflected water flows in the downstream. So part of the water flowing after reflection is completed. After the reflection is completed, that you call it as what? The reflected water. So you throw a stone in this normal flow of water. A part of the water still flows in the downstream even though you have thrown a stone. Name it as incident water. And a part of the water is reflected, and after the reflection is completed, the water flows in the downstream. You name it as reflected water. So in total, what is the water transmitted in this section? Incident water plus reflected water. So in total now, what is the transmitted water? Incident water plus reflected water. Similarly, you observe the transmission line. connect some load here. Line impedance ZC. Now why you get the reflections in a transmission line? You got reflections here because we have thrown a stone in the water flow. Then why you get the reflections in a transmission line? The reflections in a transmission line are due to change in impedance. So here characteristic impedance ZC, here load impedance ZL. As you have a change in the impedance, you have reflections in transmission line. So the first point is reflections in a transmission line are due to the change in the impedance. Are due to change in impedance. Suppose the load impedance is same as characteristic impedance, then do you have reflections? You don't have reflections. So a transmission line without reflections is known as flat line or an infinite line. Flat line or an infinite line. So what is the next point? A transmission line terminated with ZL equal to ZC is known as flat line or infinite line. So as ZL equal to ZC, flat line do not have reflections. So what we say now? Therefore the flat line or infinite line do not have reflections. And now you come across incident waves. The next term is incident waves. So how the incident waves travel from sending end to receiving end of transmission line? Incident waves travel from sending end to receiving end of transmission line. So incident waves travel from the sending end to the receiving end of a transmission line. And how you write that incident current? I is equal to incident voltage is V divided by what is the impedance of the line? The characteristic impedance ZC. Now, the waves traveling from receiving end to sending end are known as reflected waves. Are known as reflected waves. So now you say that the reflected waves travel from receiving end to the sending end of a transmission line. So what about the reflected current I dash? It is reflected voltage V dash, where they travel through the line. What is the impedance of the line? The characteristic impedance ZC. But observe, I and I dash, are they flowing in same direction? They flow in opposite direction. As they flow in the opposite direction, assign negative sign. Assign negative sign. Now, what about transmitted waves or refracted waves? They flow through load impedance. They flow through load impedance. So you say refracted or transmitted waves travel through the load. So how much I double dash is? Transmitted voltage V double dash divided by what? Load impedance Z. So this is regarding transmitted waves, I double dash here. And earlier you have written the point. What is transmitted water? Incident water plus reflected water. Similarly, transmitted current is incident plus reflected. Transmitted voltage is incident plus reflected. So all these relations are satisfied for current and voltage waves also. So this is the concept of traveling waves. So why you get reflections in a transmission line? Due to change in impedance. And a transmission line terminated with load impedance ZL equal to ZC is known as flat line or infinite line. Therefore, a flat line or infinite line do not have reflections. And incident waves travel from sending end to receiving end. Reflected waves travel from receiving end to sending end. Refracted waves travel through the load. And these are the relations further applicable. And now we analyze the transmission line for different conditions. So initially you consider the receiving end of transmission line operating under no load condition that we implement as case 1. So receiving end of transmission line operating under open circuit conditions. So indicate incident VI, reflected V dash I dash. What about no load? For no load condition, what about the current I is equal to 0? Now, if the current flowing through receiving end, as the receiving end is open circuit end, is 0. So which energy is 0? Electromagnetic energy stored by inductor in the magnetic field is 0. So which energy is 0? Electromagnetic energy stored by inductor in the magnetic field. Half Li square is 0. Then what about electrostatic energy stored by capacitor in the electric field? You have half CV square. You have half CV square. Now, according to law of conservation of energy, can you destroy energy? You cannot destroy energy. Only you can convert energy from one form to another form. So according to law of conservation of energy, we cannot destroy energy, but we can transfer energy from one form to another form. So instead of saying electromagnetic energy is 0, you say that entire electromagnetic energy is converted into electrostatic energy. So according to law of conservation of energy, it is not possible to destroy energy. Only you can convert energy from one form to another form. So instead of saying electromagnetic energy is 0, we say electromagnetic energy is converted into electrostatic energy. Converted into electrostatic energy. Due to that, what happens? The electrostatic energy increases. That means half CV square increases. How it is possible? Only when the voltage increases. By how much the voltage increases, you don't know. Assume as E. So the increase in electrostatic energy is due to increase in voltage. Let E be the increase in voltage. So by how much the electrostatic energy increases depends on how much the electromagnetic energy has decreased. How much it has decreased? Completely. Half Li square to 0. So half Li square. How much it increases? Due to increase in voltage E. So I, on simplifying, how much you will get? E is I into root L by C. Root L by C is Zc. What is I into Zc? I into Zc is V. So with the receiving end open circuited, the voltage at the open circuited receiving end increases by V. That means if you have a voltage wave of incident voltage wave of 10 kV traveling, by the time it reaches the open circuited receiving end, that voltage increases by the same value. So how much you get? 20 kV. So if you have incident wave of 10 kV traveling, when the incident voltage wave reaches open circuited receiving end, it increases by the same 10 kV, you get the voltage 20 kV. So the meaning of this is, with the receiving end operating under open circuit condition, the voltage at the open circuited receiving end increases by V. For example, if an incident voltage wave of 10 kV travels through the line and reaches the open circuited receiving end, then voltage at the open circuited receiving end increases by the same 10 kV. So voltage is 20 kV. So now we find the coefficients of reflection, coefficients of transmission for both voltage wave and current wave. So what about first? We draw for current wave and then for voltage wave. First is for current, other is for voltage. Say length of the line is some L. First to consider t equal to 0 minus, that is the instant before current wave begins to travel from sending end of transmission line. And what does t equal to 0 indicates? The instant at which current wave begins to travel from sending end and the instant at which voltage wave begins to travel from sending end. What about 0 plus? The instant after current wave has traveled a distance from the sending end and the distance after voltage wave has begun to travel from sending end. Now you travel the length of the line. So what is the current you get now? I. Now travel the length of the line. What is the voltage at the receiving end? It is V. So what is t equal to 0 minus? The instant before voltage wave begins to travel or the instant before current wave begins to travel. What is t equal to 0? The instant at which voltage wave commences to travel or the instant at which current wave commences to travel. What is t equal to 0 plus? The instant after voltage wave travel from sending end or the instant after current wave starts traveling from sending end. After traveling the length of the line, at the receiving end current is I, at the receiving end voltage is V. But you are dealing with the no load condition. What should be current at the receiving end? 0. But you are having I. So how to make this I to 0? You can make I to 0 by reflecting a current wave of minus I. You reflect a current wave of minus I. And what about voltage? How to make it V to 2V? It is 2V. Now you come back to the sending end. That is, you have traveled length of the line twice. So I is equal to 0. What about the V now? V is 2V. What about the V? It is 2V. Now, at the generating station or at the sending end, can the current be 0? Current wave commences to travel from sending end. You cannot have I0. So how to make I2 flow from sending end? You know current flows only due to applied voltage. So apply a voltage of V. Total you get 3V. But here for current, so apply a current of how much? I here. So apply a current of how much? I here. So what about after reaching the receiving end? You get the current as I. After reaching this point, what is the voltage here? 3V. What is the voltage you get? 3V. And further you don't calculate. What is the reason? the same cycle repeats. The same cycle repeats. So, current cycle repeats after traveling how many times the length of the line? At L it is I. Again at 3L it is I. So, current cycle repeats after traveling length of the line 2 times. Current cycle repeats after traveling length of the line 2 times. At L the voltage is V. 2L voltage 2V. At 3L voltage 3V. If you travel the length of the line n times, then what is the voltage? NV. So voltage after traveling length of the line n times equal to N into V. So voltage after traveling length of the line n times equal to N into V. Now you find the coefficients now. Reflection you write it as rho for current rho I, voltage rho V. Transmission is tau I, here transmission is tau V. Rho I, tau I, other is rho V, tau V. Every coefficient you calculate with respect to incident only. Here incident is V, here incident is I. So how much reflected? Minus I. How much transmitted? 0. Here how much reflected? V. How much transmitted? 2V. So this is how you find the coefficients. For verification, what we write now? Rho V plus rho I equal to 0. And further, tau V plus tau I equal to 2. Verification, rho V plus rho I equal to 0 and tau V plus tau I equal to 2. And those results are valid for any condition. These results are valid for any condition. So these are the points related to open circuit condition here. So again we reveal the first points, whatever we have discussed. You are dealing with the open circuit conditions. So the electromagnetic energy stored by the inductor in magnetic field, how much? Half Li square is 0. Next, electrostatic energy stored by the capacitor in the electric field, how much? Half CV square. But according to law of conservation of energy, what is it you can state there? Energy can never be destroyed. But only can be converted from one form to another form. That is, electromagnetic energy is converted into electrostatic energy. So due to that, what happens? You say that electrostatic energy increases. How it will increase? Due to increase in the voltage. How much increase in voltage? You don't know. You say, let small e be the increase in voltage. Let small e be the increase in voltage. So by how much electrostatic energy increases? Same as how much electromagnetic energy has decreased. Completely decreased. What about this one? Half CV square. But increase is due to which voltage? Small e. On simplifying, I how much you get? ZC is capital V. And further, how to check this results? Whatever you get, rho V plus rho I 0 and tau V plus tau I is 2. So these are the points related to our condition 1. Open circuit condition. And further you can say that with the receiving end open circuited, voltage at open circuited receiving end increases by V. What is that V? Incident voltage. Increases by the incident voltage. So this is the case 1 open circuit condition. Now you come across the case 2. What about case 2 now? You check other extreme, that is short circuit condition. Now check the other extreme, the short circuit condition. So consider a transmission line with the receiving end. What about now? Short circuited. So receiving end short circuited means what will be 0? Open circuit current 0. Short circuit means voltage is 0. So indicate the incident VI, reflected V dash I dash, transmitting V double dash I double dash. Now accordingly you modify the statements related to short circuit condition. If voltage is 0, which energy will be 0 now? Electrostatic energy stored by capacitor in the electric field is 0. So electrostatic energy stored by the capacitor in the which field? In the electric field. Half CV square is 0. Then what about electromagnetic energy? Electromagnetic energy stored by the inductor in the magnetic field. Electromagnetic energy stored by inductor in magnetic field, half Li square. Now, according to law of conservation of energy, energy can never be destroyed, but only can be converted from one form to another form. That means, in this case, electrostatic energy is converted into electromagnetic energy. So as a result, what happens? Electromagnetic energy increases. Why it will increase? Due to increase in current. You don't know what is the increase in current. You say the increase in current is some small I amperes. Now we find I. So by how much this electromagnetic energy increases? Same as how much the electrostatic energy decreases. So by how much it has decreased? Completely. Half CV square to 0. So it has decreased completely. Half CV square. It will increase half L I square. So what is I now? V by root L by C. V by ZC is capital I. So what is the meaning of I equal to capital I? Suppose you have an incident current of some 11 kiloamperes. By the time you reach the short-circuited receiving end, current increases by the same 11 kiloamperes. You get 22 kiloamperes now. So with the receiving end short-circuited, what we conclude? Current at short-circuited receiving end increases by capital I. What is that in capital I? It is the incident current. Increases by capital I, that is incident current. Now similarly you can check the coefficients for this current voltage waveforms now. So only we change the axis here. Now voltage and here current. Now voltage, now it is current. So first t equal to 0 minus, what we indicate? The instant before voltage wave begins to travel or current wave begins to travel. T equal to 0, the instant at which voltage wave commences to travel and the instant at which current wave commences to travel. Now t equal to 0 plus, the instant after voltage wave begin to travel and the instant after current wave begins to travel. Now once you reach the receiving end, voltage is V and current is I. But with receiving end short circuited, what is the voltage at the receiving end 0. So how to make V equal to 0? Reflect a voltage wave of minus V. You get V equal to 0. But what about current? Increases by the same value. You have I. How to make it 2I? Reflect plus I. Now they reach the sending end V0. Here at the sending end 2I. But sending end, can the voltage be 0? Sending end means generating station. Voltage cannot be 0. So a voltage wave is applied, due to that current wave flows. So total I plus 2I, you get 3I. Again they reach the receiving end V, and here it is 3I. Further you don't draw because the same cycle repeats. Further you don't draw because the same cycle repeats here. So almost the nature of the waveform is same, but only the change in the axis. Now what are the coefficients of reflection? Rho V, here rho I, and transmission coefficients tau V, and here it is tau I. What is the denominator? Incident voltage V, incident voltage V, incident current I, here incident current is I. So how much is reflected? Minus V. It is minus 1. How much transmitted? 0 is 0. How much is reflected? Plus I. It is plus 1. How much is transmitted? 2I. It is plus 2. So how to make this? Rho V plus rho I is 0. And tau V plus tau I is 2. Rho V plus rho I is 0. Tau V plus tau I is 2. Now voltage cycle repeats. After traveling length of the line how many times? At L it is V. Again it is V at 3L. So voltage cycle repeats after traveling length of the line 2 times. Further you check please. At L current is I. At 2L current is 3I. At 3L current is 3I. That means current after traveling length of the line n times. How much? N into I. Current after traveling length of the line n times. How much? Equal to n into I. So this is regarding our first two conditions, open circuit condition and short circuit condition. And for both, these relations are satisfied. These relations are important. Whatever question may be asked in the examination, you calculate, but they should satisfy these relations. So these relations are valid for any data given in the question. Okay, now you have 5 minutes break. First question is by Arijit from Kolkata. What is condition for distortion-less transmission in long line? Now, in this topic we come across that after say 1 or 2 hours further. Next question is by Shailesh from Bikaner. We always rate the transmission lines according to voltage basis. Why don't we rate it on the base of current? Now, your question is good. On either side of a line, what you will have? This side step-up transformer, this side step-down transformer. Step-up transformer you classify based on increase in voltage. Step-down transformer you say based on the decrease in voltage. So line is between two voltages. So always the line's voltage ratings are important rather than the kVA ratings or current ratings. A practical network has step up on other side, step down on other side. So in between we have a line with different voltages on either side. So they are rated in terms of voltages. Next question is by Shailesh from Bikaner. If there are no losses in power transmission through DC, why don't we use such system? No, DC has all advantages only when compared with AC. But still it is only in the process of establishing. So mostly by the year 2025, at least 60% of lines in India are DC, will be DC. And whenever we see at the transmission lines, they are like just carried from one pole to another. They are simply connected in one particular connection. How can we say that they may be in parallel cascade? No, the poles you can assume like a railway track. On a railway track, a train can travel in any direction, whichever direction you want. Same is with power flow also. It can be flowing through the line in either of the two possible directions. Series cascade you cannot identify place. It depends only at one particular line. They make it cascade. Line extended, how to know it is extended line or a single line? That we cannot identify place. Next question is by Narendra from Hyderabad. For calculating SIL, do we need line values or phase values? Voltage is line-to-line value place because you calculate SIL or CIL for all three phases together, not for one phase. So take only the line values and substitute and calculate. Next question is by Arijit from Kolkata. What is the equivalent series impedance in long line equivalent circuit? Characteristic impedance only please. Series impedance there also R plus JXL only. This question is Arpita. Please explain the concept with water example. No, you throw a stone in the water flow. What happens? A part of the water still continues to flow without getting reflected. So the water flowing in the downstream without getting reflected is incident water. And a part of the water is reflected. You know that reflection is very temporary. After the reflections are completed, again that water flows in the downstream. So the water flowing in the downstream after reflection is completed is reflected water. So at any time what is the transmitted water? The water that is flowing without getting reflected, that is incident water, plus the water flowing in the downstream after reflection is completed, that is reflected water. Next question is by Sanjog. In open circuit condition, I becomes 0, V becomes 2V. But at the sending end, can the current be 0? Generating station side, you have some current. But how current flows? Only when voltage is applied. So, you apply a voltage V, it becomes 3V, current becomes I. So, when the receiving end is obtained, current is I, voltage becomes 3V. Next question is by Sanjog. Can you explain after T equal to TL? TL plus, check here, in short circuit voltage 0, but we have V. How to make V to V 0? Reflect a voltage wave of minus V. And current increases by I, you get 2I. How to make I to 2I? Reflect a current wave of I. Next question is by Arpita. It means in open circuit line, terminal voltage will keep on increasing with time. It's absolutely correct. Next question is by Arijit from Kolkata. Please explain the traveling of waves at various instants of time once again for open circuit. See, open circuit cannot redraw. You can understand short circuit. Based on that, you develop open circuit. Similar explanation. So, you reach the receiving end, voltage is V, current is I. Receiving end short circuited. So, how to make voltage 0? Here voltage is V. How to make V 0? Reflect a voltage wave of minus V. And current increases by I, you get 2I. How to get I to 2I? Reflect a current wave of plus I. So you get V0 at sending end, you get 2I at the sending end. But generating station, can the voltage be 0? 11 kV always. So apply a voltage V, here you apply a current I. Total how much you get? 3I. So you reach the receiving end V, reach the receiving end 3I. Similarly, you can apply for open circuit, please. Next question is by Arpita. Direction of power flow depends on the load angle. How can we change the load angle? No, it depends on delta minus beta, please. Beta minus delta. Okay. So direction of power flow, not only delta, please. It is beta minus delta. Beta means what? Beta is the impedance phase angle of transmission line. Impedance phase angle of transmission line. And how you can change load angle? See, that is a part of power system stability, please. Okay, but still, you can change the load angle delta by making beta minus delta positive or negative or 0. If the difference is 0, maximum power is transmitted. Next question is by Arijit from Kolkata. Please explain what happens at T equal to T plus in travelings, either for open or short circuits. At T equal to TL plus. Here voltage is V. Short circuit voltage must be 0. How to make V to V 0? Reflect a voltage wave of minus V. So you get V 0. But due to short circuit, current increases by I. How to make I to 2I? Reflect a current wave of plus I. Reflect a current wave of plus I. So now you come across case 3. Now where the receiving end of transmission line is terminated with resistance. Case 3 is the receiving end of a transmission line terminated using resistance. So you consider the transmission lines, consider the resistive load now. Indicate the incident VI, indicate the reflected V dash I dash, indicate the transmitted V double dash I double dash. Impedance of the line is ZC. So what is the incident current I? V by ZC. What is the reflected current I dash? Minus V dash by ZC. What is transmitted current I double dash? V double dash by R. So now you also know the relations. Transmitted is incident plus reflected. Same for current also. Incident plus reflected. Now first our objective is to find the reflection coefficients. So use the relation I double dash is I plus I dash. And substitute now. V double dash by R, V by ZC minus V dash by ZC. So V double dash by R, V by ZC minus V dash by ZC. You want the reflection coefficient. How to write the reflection coefficient of voltage? It is V dash by V. So, how to eliminate this V double dash? By writing V plus V dash. Eliminate V double dash now. How to eliminate? By writing V plus V dash. So, we write now V plus V dash by R, V by ZC minus V dash by ZC. You take out the common terms, V dash into 1 by R plus 1 by ZC, V into 1 by ZC minus 1 by R. So V dash into R plus ZC, V into R minus ZC. So V dash by V is R minus ZC by R plus ZC. So this is how you find the reflection coefficient of voltage. How to find for current? You know the shortcut formula. Rho V plus rho I is 0. So reflection coefficient of current in general I dash by I, but minus rho V. Ought you write ZC minus R by ZC plus R. So this is how you write the reflection coefficient of current here. The reflection coefficient of current. Now you find the transmission coefficients. So what is V double dash? Similarly, you write the same three lines as it is. Write the same three lines. I double dash is I plus I dash. So V double dash by R, V by ZC minus V dash by ZC. So V double dash by R, V by ZC minus V dash by ZC. So how you write the transmission coefficient of voltage? V double dash by V. So how to eliminate V dash? How to eliminate V dash from this? Write V double dash minus V. So V double dash by R is V by ZC minus V double dash minus V by ZC. V double dash, you take it common, 1 by R plus 1 by ZC. How much? 2V by ZC. So V double dash into R plus ZC. How much? V into 2R. How much? 2R by R plus ZC. This is the transmission coefficient of voltage. So what about tau V plus tau I? It is 2. But tau I as per formula, how to write? I double dash by I. It is 2 minus tau V. On simplifying, 2 ZC by R plus ZC. How much again? 2 ZC by R plus ZC here. So this is how you write the transmission coefficient of current. Among all these three formulae, in examinations, this third formula is most important. Generally, they ask us V double dash expressed in terms of V. All equations are not important. Third most important. V double dash expressed in terms of V. Now suppose you terminate the receiving end of transmission line now using what? An underground cable. Using an underground cable. So terminated through cable. So what will be I double dash now? V double dash by Z cable. So throughout the derivation, what is the only change we make? Wherever you have R, replace with Z cable. Wherever you have R, please replace with Z cable. So throughout our derivation, wherever you have R, please replace with Z cable. And other than that, no change in the analysis. So only that is the change for our condition 4, where the receiving end of a transmission line is terminated through cable. So wherever R is there, you replace that R with cable. You replace that R with jet cable. Now you come across this last case 5. So receiving end of a transmission line forming what? A T junction. This is what occurs in practice. This case 5 is what you will get in practice. That means you have a transmission line. Further, you have some loads connected in parallel, forming a T junction here. So line impedance ZC, load impedance Z1 and Z2. What about incident? You write VI. What about reflected? We write V dash I dash. But how many loads are in parallel? 2 loads. So you have 2 transmitted currents. What can be those 2 transmitted currents? I1 double dash and here I2 double dash, and transmitted voltages V1 double dash, V2 double dash. As the loads are connected in parallel, the voltages are equal. So V1 double dash, V2 double dash, same as V double dash. And a transmission line terminated with at least 2 loads connected in parallel further is known as what? Bifurcated transmission line. So bifurcation means separation. So a transmission line further separated or further with 2 loads connected, at least connected in parallel, is known as what? Bifurcated line. So first we write its definition. What is this bifurcated? A transmission line with at least 2 loads connected in parallel. So what is I equal to now? V by ZC. What is I dash? Minus V dash by ZC. 2 transmitted currents, I1 double dash, V1 double dash by Z1 or V double dash by Z1. I2 double dash, V2 double dash by Z2 or V double dash by Z2. What about total transmitted current? I1 double dash plus I2 double dash, or it is incident plus reflected. But V double dash is incident V plus reflectant V dash. And so again we find the reflection coefficients first. Use our basic relation. I1 double dash plus I2 double dash is I plus I dash. So V double dash by Z1, V double dash by Z2, V by ZC minus V dash by ZC. So V double dash into what we write? 1 by Z1 plus 1 by Z2. V dash outright, V double dash so you are finding the coefficients of reflection. So we have to eliminate V double dash. How to eliminate V double dash? By writing V plus V dash. You take out V dash terms common. 1 by Z1, 1 by Z2, 1 by ZC. V term common, 1 by ZC minus 1 by Z1 minus 1 by Z2. So reflection coefficient of voltage is V dash by V. And denominator is the same. The equation 1. Now how to find the reflection coefficient of current? Rho V plus rho I is 0. As per rho I, it is I dash by I. You write minus rho V. So how to write this rho I now? 1 by Z1 plus 1 by Z2 minus of this value. Denominator is the same. So next one is the transmission coefficients. First three lines are as it is. So we rewrite the same three lines as it is now. So what about this I1 double dash? V double dash by Z1, V double dash by Z2, V by ZC minus V dash by ZC. So V double dash you can take it common, and here V by ZC minus V double dash minus V. Now you take out the common terms V double dash, 1 by Z1, 1 by Z2, 1 by ZC. What about V? 2V by ZC. So what is the transmission coefficient of voltage? V double dash by V. How much you get? 2 by ZC by 1 by Z1, 1 by Z2 plus 1 by ZC. Please make a note of this. End relations are important. Among these three, the third one is the most important equation. What is V double dash in terms of V? How to find the transmission coefficients of current? You make use of this equation now. So V double dash can be written as V1 double dash. So 1 by Z1, 1 by Z2, 1 by ZC. So what is V1 double dash? I1 double dash Z1 V how much? I into ZC. So what is the transmission coefficient of current? I1 double dash by I. How much you will get? 2 by Z1 denominator, 1 by Z1, Z2, ZC. Now use the same equation now. Instead of V1 double dash, you can write V2 double dash also. Instead of V double dash, now you can write V2 double dash. Similar equation. Here it is 2V by ZC. So V2 double dash is I2 double dash Z2. Further you have to simplify this. V is I into ZC. So what is the transmission coefficient of I2 double dash? I2 double dash by I. How much? 2 by Z2 whole divided by 1 by Z1 plus Z2 plus ZC. But among this total 5 equations, the equation 3 is most important. Among all these equations, the equation 3 is most important place. So practice the equation 3 of case 3, case 4 and case 5. So please practice. No need of practicing the derivations. Only the equations 3 in each case 3, case 4, case 5 are important. You try to remember the formula, that is more than sufficient. But how to evaluate is what we have discussed here in case 3, case 4 and case 5. So with this we conclude today's session.